So today we're looking at CFCs. This is your checklist, so come back to this at the end and see if there's anything you need more clarification on, and you can let me know. So CFC stands for chlorofluorocarbon. So the definition for this, the clue is in the name, is that it's a family of compounds that contain chlorine, fluorine and carbon atoms. And in the other information box over here, they were originally invented to replace ammonia that was a coolant in fridges, because ammonia is toxic and corrosive and CFCs are not. Some examples, I have two over here. So where we get these from is that they are alkanes where all of the hydrogens have been replaced by chlorines and fluorines. So you can tell on both of these, there's only one carbon in the middle. So these would both be methane. And what has happened to the methane is all of the hydrogen atoms have been removed, and instead we have chlorine and fluorine atoms on there. So to name this, we've named chloroalkanes before, so it's very similar to that. In the first one in the green box, we've got 3 chlorines, so that will be trichloro. We've got 1 fluorine, so that will be monofluoro or just fluoro. And we write them down alphabetically. So that would be trichloro, monofluoro, methane. The other one is methane as well, but this time we've got 2 of each of chlorine and fluorine. Again, we name them alphabetically, so it will be dichloro, difluoromethane. And you are asked to give an example of a CFC sometimes. You could choose any alkane, draw it out, replace all of the hydrogens with chlorines and fluorines, and just name it correctly so that you've got 4 bonds from each carbon. The uses of CFCs, this comes up and they'll ask you what were they used for before the restrictions were brought in, when we figured out that they cause ozone depletion. And the uses are as refrigerants or coolants in fridges and freezers, so to keep things cool. They were used in air conditioners and in aerosol propellants. So in an aerosol can, like a deodorant can, you've got the gas in the canister, and when you want to spray it out, it's a CFC that was used to propel it out of the can. Some properties: they have low toxicity, low boiling points and low flammability. That's the perfect combination if you want something that is very unreactive and very stable. And that was the criteria for finding something to replace the ammonia, because the reason we didn't like that was because it was toxic and it was corrosive. So that was a very good thing for the CFCs in terms of replacing ammonia. However, when it's released into the atmosphere is when it becomes dangerous. So it's stable in the lower atmosphere, but this stability means that it has a long residence time. And that means that it stays in the atmosphere for a long time, approximately 100 years. And they want you to know that as well. And what that means is that this allows time for the CFC molecules to transport further up into the atmosphere and get into the stratosphere, where we know the ozone lives. And up there they do become reactive. They become reactive for the same reason the oxygen is reactive up there, because of the UV light, and we'll get onto that in a second. The questions you could be asked on what we've done so far, so this is kind of summarizing what you need to know nicely. First of all, what are CFCs? You need to know that they are chlorofluorocarbons, or compounds that contain chlorine, fluorine and carbon. Why do CFCs have a long residence time in the lower atmosphere? The reason for that is their stability, or the fact that they are unreactive. It's also due to the fact that there's no UV light, there's very little UV light in the lower atmosphere to break them down. That's what we're going to go on to next. Name any CFC. I've listed the 2 that we mentioned earlier for methane. However, you could choose any alkane, and as long as you've named it correctly, that there's all chlorines and fluorine atoms on all of the carbons, you would be fine. Give a major use of CFCs in the past, before restrictions would have been introduced. We said refrigerants, as in air conditioners or in aerosol propellants. When a CFC compound enters the stratosphere, the upper atmosphere, it can be broken down by UV radiation. So this is photodissociation again. Here we've got CCl3F. When that is exposed to UV radiation, we produce a chlorine-free radical, the Cl with the dot there, a chlorine-free radical. And that's the main cause of ozone depletion, that chlorine-free radical, because it's very reactive and it will attack an ozone molecule when it comes in contact with it. And that will produce oxygen and the ClO, chlorine oxide free radical. That free radical that's produced in the blue there, the ClO, that can then go on to react or attack an oxygen free radical. And by that reaction, we reproduce oxygen and we regenerate our chlorine-free radical. And that's extremely dangerous because that chlorine-free radical can then go back and repeat reaction 2 in blue there. It can repeat that and then repeat step 3. And what we've got is a chain reaction here. And that means that one single chlorine atom can destroy tens of thousands of ozone molecules. The questions that summarize all of that, so describe how CFCs are broken down in the stratosphere. You could say by photodissociation, by UV light, UV radiation, or you could write a sample equation for that. The green and yellow question are basically the same thing here. In green, it's asking you to explain, so I've done that in words. In yellow, it's stating to use equations. So I've given it to you in words and using equations, how CFCs or chlorine radicals cause ozone depletion. So first of all, the green one. CFCs release chlorine-free radicals that attack ozone molecules. A chain reaction is set up which regenerates chlorine-free radicals to continue attacking ozone molecules. Then in the yellow, we're just going to basically say all of that using equations. So we've got ozone and the chlorine-free radical, and then they are producing oxygen and ClO. The ClO will then react with an oxygen-free radical to regenerate the chlorine-free radical. This creates a chain reaction which allows the process of chlorine attacking ozone molecules to keep repeating itself. So hopefully that makes sense to you. If not, do let me know. It's a hard concept. You could also be asked to name an oxide that causes ozone depletion. And the only one we are going to study is nitrogen monoxide. So if they ask you for an oxide that causes ozone depletion, it would be this. And the reaction is there for you. They haven't ever asked the reaction, but just note that anything that is causing the depletion of ozone, anything reacting with ozone, is going to have oxygen produced. And then you can put the rest together, that you've got NO and another oxygen from the O3 to make NO2. You need to know sources of nitrogen monoxide, and your sources will be from microorganisms, the reactions that go on in them, from lightning. That's all you would need to say, but just to explain that a bit, we saw it earlier in the chapter, that when there's an electrical discharge, a lightning strike, it can cause nitrogen gas and oxygen gas from the atmosphere to react together, creating nitrogen monoxide. And it's also produced in exhaust fumes if a catalytic converter isn't working efficiently. It is important to note that nitrogen monoxide is not the main cause of ozone depletion. CFCs, or chlorine, have a far more significant impact, so they're the main cause of ozone depletion. But nitrogen monoxide is an oxide that causes it. This is in other information, the stuff on methane. I've written it down here at the bottom. It's actually not on the syllabus and it hasn't been asked, but for some reason they haven't removed it from the book, so I like to just quickly go over it, even though I don't think you'll be asked it. So methane, we discussed it as a greenhouse gas, but it also has a benefit in the atmosphere as it helps slow down the rate of ozone depletion by removing chlorine-free radicals. And how it does that is by this equation here on the slide. Methane will react with a chlorine-free radical, forming hydrochloric acid, which will then be precipitated in the rain. So that will dissolve in rainwater and fall back down. This is extremely important in preventing the buildup of the chlorine-free radicals in the stratosphere, which will then slow down the rate of ozone depletion. So that's one way that the chlorine-free radicals can be removed from the stratosphere, preventing them from breaking down the ozone. We have seen that CFCs have very negative impacts on the ozone layer. So we need to find substitutes for them. The main substitute that we have at the moment are a group of compounds called HCFCs, hydrochlorofluorocarbons. I'm showing you a very simple one here. The simplest one is chloro-difluoromethane, and that's a propellant used in aerosols that can be marked as ozone friendly because it has a lesser impact on ozone depletion than CFCs would. And the reason for that is because the carbon to hydrogen bond that you can see there can be broken down in the lower atmosphere. So that can be broken down to form a free radical much lower in the atmosphere, which will prevent, for the most part, the chlorine containing compound reaching the upper atmosphere. So we form the free radical lower down in the atmosphere, hopefully removing the chlorine compound from traveling upwards into the stratosphere, where it could be used to attack ozone. They are not the perfect solution. Obviously, they still contain chlorine, and there is a chance that is going to then reach the stratosphere and cause ozone depletion. So they're not perfect in that sense, and they are also a greenhouse gas. So even with that, they're still better than the CFCs. They have around 5 to 33% of the effect, so a much lesser effect than CFCs. And there is a lot of research going on into HFCs, so hydrofluorocarbons, where there would be no chlorine atom present in the molecule. The questions that go with that last few slides would be: name the oxide associated with ozone depletion, nitrogen monoxide. Give a source of this oxide. We went through those microorganisms, lightning and exhaust fumes. And what is the main compound responsible for ozone depletion? It's not nitrogen monoxide, it would be CFCs, or the chlorine-free radical. Name the group of gases replacing CFCs. That would be HCFCs. Why are they less damaging than CFCs? They're broken down before they reach the stratosphere, so the chlorine doesn't reach the stratosphere. And the reason for that is the carbon to hydrogen bond has a lower bond energy, and that will break lower in the atmosphere. And why is research being carried out to find a replacement for HCFCs? The reason for that is that they're not perfect. They are a greenhouse gas. They still contain chlorine, which will still have an ozone damaging effect. And ideally, we want to get rid of all chlorine containing compounds that may enter the atmosphere. So that's the end of this video and the end of the chapter.